Good morning, all. Welcome to the world of thermal energy. So let's go through a bit of background before we get started. So this first slide, no, you don't need to copy it down. It's just a bit of background just with regards to how we understand temperature. In fact, this is just the nature of all science, right? Because science always starts off with somebody having an idea, and then the person exploring the idea and proving or disproving whether it's correct or not. So in the world of thermal energy, as funny as it may sound, guys, you guys may only be familiar with two different types of thermometers, right? The Celsius and Fahrenheit. And if you've taken chemistry class, you probably learned a third one as well. But in truth, temperature thermometers are all based upon the inventor, and there are dozens of inventors of thermometers, even Sir Isaac Newton himself. However, at the end of the day, only a handful of them came out at the end. All right. Even our understanding of temperature has evolved over time. So this stuff that you're reading in blue, it's a story of Antoine Lavoisier, a famous scientist, where he first thought that, hey, you know what? Let's imagine heat as this invisible, massless liquid. And it seems to make sense, right? Like, for example, if your friend's coming from the outside and they're all cold and they give you a big hug, suddenly you start to feel cold because something's being drained out of you. And according to Antoine's theory, he says that this invisible heat called caloric fluid flows out of your body and flows into your friend's body, all right? So that's why you suddenly feel cooler. Also, if you stand on a scale, you'll notice that your mass doesn't change in that state. So he said it was this invisible massless fluid that would flow from body to body. But it could not explain this one thing, though. Why does this generate heat? How do you get caloric from nowhere? And that's the reality of all theories, all right? Theories, they may explain what's going on at that time, but somebody else may say, hey, wait, there's a catch to this, and then it gets refuted. So today, our understanding of temperature is now understood through this theory called the kinetic molecular theory, concept that you've covered in the past few years in science class. So let's go through that one more time, all right? Where the kinetic molecular theory states that all matter is made up of particles, atoms, molecules, however you want to call it. But here's the interesting thing. These atoms or molecules, or bunches of atoms all together, they're not stationary as long as you're above absolute zero. All right, so they're constantly moving, they're constantly jiggling. In fact, the faster they jiggle, the higher their overall temperature. All right, there was another scientist, and his name was Robert Brown, and he was the first to observe this weird phenomenon. There was one afternoon, he was just sitting outside on his porch enjoying a cup of tea, but when he was looking at his tea with the leaves in there, he noticed that the leaves or the little seeds in there, they were moving around, even though he didn't touch the cup at all. And I don't know if you guys ever observed that before, right? Hot water, you'll always see that bubbly movement in the water itself, and you place something as a trace particle inside, like for example, food dye, you'll notice that the food dye will start swirling around, all right, indicating that molecules are constantly moving. And the higher the temperature of the molecules, the faster the fluid moves, and the slower, the lower the temperature, the slower that the molecules move, and the slower that it's going to stir your tea or whatever it is in your cup. Okay. This kinetic molecular theory also covered a few other ideas. It's also able to explain the different states of matter. All right. Again, if everything's constantly in motion, then when it's moving slow enough, there's a chance for the atoms to bond and stick together. And this is when we have the state called a solid. You keep on adding up more and more of this thermal energy, and suddenly they start moving so fast that they break off each other, but still somewhat coheres with each other. All right. And in this case over here, as they fall apart but still are able to somewhat stick together, this is the concept of a liquid state. All right. A student, you raised your hand a few times. You had a question? Okay, just watch out for your keyboards. All right. And now as you continually increase the temperature of the atoms, they move so quickly that they just simply bounce off each other. They don't stick anymore. And in this new state, it's known as a gaseous state. All right. In fact, with the gaseous state, if you've observed balloons before, balloons inside of them, it contains pressure. And the pressure is a result of these molecules bouncing off each other, whacking against the wall of the balloon itself. All right. So the kinetic molecular theory is able to explain all of these concepts here. And again, that one key number that I mentioned earlier is that as long as you're above this temperature, the molecules are moving. But once you hit this temperature, that's it. All particles stop moving. And that happens at negative 273.15 degrees Celsius. I think just around it, to keep things simple, often it's just called negative 273, and we'll call it a day. All right. And since that's the lowest temperature that's ever possible, that's when we end up resetting our number scale, and we just call that point in the temperature scale as absolute zero. And you've probably heard of that term before, right? That's the lowest temperature that's ever possible. We can't get a temperature lower than that because the definition of what temperature is the average kinetic energy of the molecules while they're in motion in a substance. And there's the definition. Okay, temperature is a method to measure the average kinetic energy of all the particles in a quantity of matter. All right, and as I mentioned, there are many different scales out there. The one that we stick with today is the Celsius scale. And again, we want to make a scale that's universal. So in other words, if you break the original thermometer, you can reinvent the thermometer again. So this is the standard that we go by. In fact, most standards come from references to water because it's so abundant. All right. So if you get fresh distilled water and you try freezing it, you'll notice that at some point while it's freezing in the freezer, you'll see both states at once, right? You'll see the ice as well as the water both at once. And it takes a long time before it turns into complete ice. In fact, if you measure the temperature at that point there, it'll be exactly at 0 degrees Celsius. The same is also true if you take some ice cubes and you drop it in water and you stir it. All right, stir it for a minute or so and you let it stabilize. As long as you can still see ice cubes and water all at once in your cup, that's a reference of 0 degrees Celsius. They do have thermometers where there aren't any markings on it. So without the markings, the first marking you'd place is right there. All right, so that's how you reference 0 degrees Celsius. Now, as long as you're at ocean level air pressure, so at standard atmospheric pressure, then if you boil the water, you bring it up to high enough temperature, it's going to convert itself quickly from liquid into gas. All right, so that state of boiling. And during that state of boiling, the temperature stabilizes yet again. Some of you guys might have noticed that when you're doing your experiment at home. All right, and then that's where on the Celsius scale, you place another marking on top. All right, so you have the reference for 0, which is the freezing temperature of water, and you have 100 degrees Celsius, which is the boiling temperature of water, and it used to be called centigrade, right? Centa meaning 100, and that's why they took these two and they divided by 100. And that's pretty much how the Celsius scale was invented. It was originally called the centigrade scale and then was upgraded to the Celsius scale. And yes, you can convert between Fahrenheit and Celsius. Before, they had their own unique scales with no specific equation. But as I've mentioned, we always want to create standards. I don't remember the year that they created this formula, but at some point they wanted to redefine the temperature of Fahrenheit. All right, so that Fahrenheit can be easily converted to degrees Celsius using a relatively clean formula. And that's what the formulas you're seeing on the screen right now. So again, they were invented after the Fahrenheit scale was created. The Fahrenheit scale is as old as Newton, I believe. All right, so it's a fairly old scale invented by Fahrenheit. Apparently, he was a really good glass blower. All right, so he was able to fabricate these thermometers, and they were very reliable, and they could repeatedly measure temperatures over and over again faithfully. All right, and in his original scale, he wanted 100 Fahrenheit to be a healthy body temperature. Right. Today we know that if you're at 100 Fahrenheit, you're probably sick. And the only reason for that is, again, they had to squish the scale by a slight bit just so that they can have this weird conversion ratio. Okay, so it's the evolution of just creating new standards. One thing that I do want to point out right now is that with Celsius, Celsius has a very close sibling, and it's called Kelvin. I briefly mentioned this before, that there are 5 fundamental units: meters, kilograms, seconds, ampere, and Kelvin. All right, and Kelvin is the temperature that is the SI variant of it. All right, now Kelvin and Celsius, they're very similar as in their unit divisions. So in other words, as you increase by a degree Celsius, you're also increasing by a degree in the Kelvin scale as well. Right, so their increments are exactly the same. But remember, as I mentioned, that since there's such thing as absolute zero, well, then the scientists said, you know what, if there's such thing as absolute zero, why don't we just take a whole entire scale and bring it all the way down so that we don't have to deal with any negative numbers? Because as you may know, negative numbers, they may cause problems. And the biggest offender is actually 0, right? Because whenever you multiply 0 by any number, you end up canceling out things and you get to 0, right? So to avoid all of that in your calculations, they decided to reset the scale. All right, if the lowest temperature possible is at negative 273 degrees Celsius, we now call that 0 Kelvin. And since Kelvin and Celsius increment at the same rate, that means that eventually when you reach 0 degrees Celsius, you're at 273 Kelvin. So that's the story between Kelvin and Celsius. And on your screen, there's the appropriate conversion ratios. And you can practice those conversions in your homework on page 6 tonight. Sorry, on question number 6 in your homework tonight. All right, it has to do with regards to Kelvin to Celsius. One extra thing just to point out is that it's just another thing in grammar. You don't call it degrees Kelvin. You just say that, for example, the room temperature down here is at 293 Kelvin, all right, or 20 degrees Celsius. All right, so Kelvin, you don't really say the word degrees. It's just part of the grammar. All right. As I mentioned, Celsius and centigrade, they're approximately the same. They do vary, I believe, by 0.01 degrees. And it just has to go with the history of trying to calibrate things so that we can always repeat and rebuild the same thing over and over again. One cute little video just to share with you right now is that, again, we do have to be very careful with how we label things. And, this can bring up a lot of controversy, especially online with a bunch of nerds, all right? There's great controversy in this particular episode of Transformers. If it's going to play. But due to copyright reasons, it's been banned, so I guess you won't get to see it. Anyways, if you have a chance to watch it in the future, Astrotrain talks about a temperature being below negative 470 degrees down where they tried to freeze Megatron, all right? And if you look at the temperature scale, well, there's no such thing as negative 470 degrees Celsius. We know that for sure. And if you look at the Fahrenheit scale, the same argument can be said as well, right? Where 459 is the lowest possible. And and then the nerds were just bashing about with it. And so one of them said, hey, hold on a second, listen to how Astrotrain quoted what he said, right? And what he said was, whoa, it's 470 degrees below zero in there. He didn't include a unit. So for all we know, Astrotrain could be referring to Cybertronian units. And that's why it's so important for us to include units in all of our measurements, right? Because without a unit, the reader will have no idea what to interpret, and then they'll be confused, and this may lead into a future disaster because of misinterpretation. You don't need to copy it on this picture over here. This is just showing you that, yes, there are many different types of temperature thermometers, and even, where's Isaac Newton? Where's a Newton? Yeah, degrees Newton. Even he tried to create his own. The only problem is that his scale was out of whack. They made it really pretty in this diagram here, but truth is that his scale was not uniform whatsoever because he just used temperature in reference to things he could find around the house. All right, so it wasn't an exact scale. It was just a scale based upon observation, and he would just call it an arbitrary number. All right, so that's why his was dropped. Okay, I'm not sure if people are wondering, when do you start copying down things? Maybe that's the question. Can you go back for a second? Remember that everything here has all been recorded. And what is important so far right now? I think the important part really starts right here. Okay, the important part starts here. It's a live recording. Okay, so there are 3 different types of heat transfer. All right, and I hope that this is a review from back in junior grades as well. All right. The first method of heat transfer is through physical contact, also called conduction. All right. So if I still happen to fill up, for example, this cup over here with very hot water, the reason why I can feel the hot water in here, even though I'm not touching the water itself, is because the molecules of the water, they're jiggling so quickly that they're bumping against the plastic. And as it bumps against the plastic molecules start to jiggle. Now the plastic has a higher temperature and it starts jiggling the molecules on my hand. All right, so that's transfer of energy through physical conduction. All right, so if we want to avoid transfer of energy through conduction, we need to insulate it. All right, we need to place a heat insulator beside it. Now, if you're wondering, do you need to copy down this stuff in blue? No, not necessarily. But you know that a heat conductor is something that can transfer the thermal energy very quickly, and a heat insulator is something that is very difficult at transferring the thermal energy, such as styrofoam. And that's why most coffee cups are made up of styrofoam. Or if you ever looked at McDonald's cups, what do they use? If you ever dissected a McDonald's cup, you'll notice that the McDonald's cup is double layered, right? There's paper, there's an air gap, and another piece of paper. Air is a pretty decent thermal insulator, okay? And if you want to improve that even more, well, get rid of the air as well. There are those fancy thermoses. They're hard to get in Canada now, but if you had one imported from your parents' hometown, you'll notice that they can hold on to either very hot water all day long or ice cold water all day long, regardless of the outside conditions. All right, and that's because those are the special ones where they vacuum chamber between the 2 environments. All right, so the inside is separated by a gap where there's no air or a lack of air. On top of that, if you ever look inside a thermos, it's all shiny inside. All right, and that has another purpose as well. Remember that heat transfer can happen one of three ways, either by conduction, convection, or radiation. All right. So any body that emits heat, like you or me, we're actually emitting off radiation right now, and it's in the form of infrared radiation. You may have seen infrared cams before, where you see the body glowing all red and the background all blue. It's not that there are those colors that really exist. It's a way of converting thermal temperatures into something that the human can understand. And so the software will go off and do that. All right. So if the temperatures are above a certain threshold, it'll start marking it as red. And if it's below a certain threshold, it'll start marking it as blue. All right. And you've probably seen them in video games as well. All right. So infrared is a form of radiation. And that's why sometimes with those high-end thermoses, the inside, they cover up the glass inside on the far end with something very shiny, right, like silver. And that way it reflects all that infrared radiation back in. So that's how very high quality thermoses are able to retain the heat for a long period of time. First, there's a gap, not even an air gap, it's a vacuum gap between whatever that's in the substance and the outside environment. And number two, they've covered the inside with something that's reflective to reflect back all of the radiation. Okay, so I did skip one in between the two. There's conduction, and the next one's convection. All right, convection only happens here on Earth. If you ever tried lighting up a match before, when you light up a match, you'll notice that the flame always points upwards. It doesn't matter if you hold the stick this way or if you hold the stick this way. The flame always points up. And that has to do with the fact that when the flame is lit, it's generating a lot of heat. And as you know, warm air has a tendency to rise. And that's what creates that flame pointing upwards in all fires, right? It's the warm air rising. So no matter how you orient the source of the combustible item, the flame will always point upwards. Interestingly enough, if you do it in outer space, you're not going to see fire like this. It will look completely different. You can try that out if you ever make it to space. It's getting more affordable these days, isn't it? Right? $250,000 if you got that kind of cash lying around. Okay, so convection, yes, it only works because there's gravity on Earth. Without gravity, convection will not work. The idea of convection is that anytime you heat up a substance, even if it's water, as you heat it up, the molecules of the water jiggle faster and faster. In other words, the density of the substance decreases because they need more space to do their little workout routine. Okay, so the density of warmer water is lower than the density of cooler water. Since the Earth or gravity loves things that are more dense, that's why rocks sink in water, it's going to drag and pull down anything that's more dense, such as the cool water. So that's why the cool water gets pushed down and the warm water will rise, and that's what convection is. You probably experience the same thing too if you own a lava lamp at home. Lava lamps operate under the same principle. There's an incandescent bulb down below generating lots of heat. The heat melts a special type of wax. And once the wax warms up, its density decreases to the point where it's more buoyant than the special fluid that's inside. It's not necessarily water in there. It's some weird chemical mixture in there. But it's in such a ratio where when the wax is cool, it's more dense than that special fluid. And when the wax is warm enough, it's less dense than the fluid. And that's why it's going to start rising. In fact, it's not that it's rising. It's that the more dense things push downwards and squeeze it up. Kind of like when you need to squeeze toothpaste to the top of your tube. That's effectively what's happening. If you ever owned an aquarium before, you've probably experienced that as well, right? You always have to aerate your aquarium with that bubble making thing. And why do the bubbles go up? It's not because they're going up. It's because the Earth loves the water and it's pushing the water down, squishing the air, so it has no choice but to go up. And that's what's really happening. And that's why at the end of the day, we have solid things on the ground, then water on top, and then air above. It has to do with regards to the density of the substance. Okay, and the last form of heat transfer, as I mentioned, is radiation. Right? It's energy that's emitted usually by electrons jumping from a higher excitation state to a lower excitation state. Something that we'll discuss in more detail in grade 12. For now, you just need to know these definitions. What is conduction? Give an example of it. What is convection? Give an example of it. What is radiation? Give an example of it. Any other questions before we move on? Again, I encourage for you guys to please read your textbook. These things have already been mentioned in your textbook from pages 270 through 289. So if you haven't had a chance yet, please go through reading through them. Okay, it may give you more examples of these guys over here. Okay, now I did ask for you guys over the the weekends to do this crazy experiment, right? Where you take you take an ice cube or a bunch of ice cubes, you fill it up into a pan, and then you gradually heat it up, right? And you might end up having a graph that looks weirdly like this. Okay, so this is temperature versus, and in your case, it'll be temperature versus time. But in truth, as time goes by, you're adding more energy to the system. If you ever looked at your stove has a certain wattage, right? Watts are measured in joules per second. So the wattage of your stove multiplied by seconds will give you joules. So really, the horizontal axis is really a measurement of energy. All right, but if you measure it as time, that's fine, but that's because you know that energy is equal to power times time. Okay, something that we covered last week. All right, so that's why the horizontal axis is really energy. And on the vertical axis, again, you always label your graphs as the dependent versus the independent. All right, and if you want to call it y versus x in your head, you're more than welcome to. All right, so the temperature is here on the vertical axis. Just want to offset things a bit because I want to have a reference of 0. Okay, now depending upon the equipment you have at home, many of us may not be able to measure what I'm going to show you right now. Instead, you probably just started off measuring values at 0. But truth is that if your freezer is set at negative 20 degrees Celsius, then you have ice cubes that are at negative 20 degrees Celsius. And the moment you put it into that pot and you heat it up, the temperature will gradually increase. So I'm not sure how many students were able to see that part of it. But I hope that you're able to see this part, that for a good, 4 to 5 minutes, it just stabilized at 0 degrees Celsius. And you're wondering, well, is there anything happening right now? But being a good kid, you just continued with regards to your lab and you just let it be because you know that eventually the ice will melt. And if you notice, the moment the ice melts, the temperature would gradually increase yet again. All right, so gradually keep on increasing until you hit this magical second value, coincidentally, at 100 degrees Celsius. Hopefully it was over this weekend because it's heavily dependent upon the air pressure in your house. All right, but it'll hit 100 degrees Celsius, and I told you that, just do the experiment for another 5 more minutes. Don't even bother after that because it's going to go beyond your screen, all right, the way how it's stabilized. And that's what you would have observed when you did the lab. If you haven't had a chance to do it, I encourage that you ask your parents to hang out with you one afternoon and just melt ice and watch it together, and you're going to see that this is the crazy outcome. All right. So why am I talking about the stuff over here? Well, if you take a look at this part of the graph, you'll notice that it's a linear correlation, right? And this is the thing that scientists have observed. Anytime you heat up a substance, it takes a certain amount of energy to heat it up. And it's fairly constant as long as you're talking about the substance in its same state, right? So again, anywhere from 0 to 100 degrees Celsius, that's H2O when it's in its liquid state, that which we know of as water. All right, so while H2O is water, it's going to gradually increase the temperature as long as you constantly add heat. All right, and that slope is really dependent upon the material that you try to melt. If it's water, it'll look like that. If you're trying to melt iron, the curve will look different, but nevertheless, it will have a measurable slope, and that's what specific heat capacity is. All right, heat capacity is the slope of that graph, where it's pretty much the amount of energy required to heat up that material by a degree Celsius. Okay, so the specific heat capacity, if you're going to jot this down, is the amount of heat energy needed to increase the temperature of a particular material by a degree Celsius, or by Celsius degree per kilogram. On course pack page 45, you'll have a lookup table of different heat capacities of substances. This is a slightly different version, but you'll get the idea across, that different materials have different heat capacities. Some items require a lot of energy to heat up, like water, and other things, such as most forms of air. I'm just looking for air. I guess that's the only example there with regards to nitrogen. Oh, air's over here. All right. Air typically has a lower heat capacity. Do you need to memorize these numbers? No, you don't need to, but I think there's one that you probably want to be familiar with because most of our experiments involve that of water. All right, so the specific heat capacity of water, if you look it up on course pack, what is it, page 45, you'll see that water, as long as it's in the aqueous state, has a heat capacity of 4.19 times 10 to the 3 joules, or roughly 4.2 times 10 to the 3 joules. Okay, roughly 4,200 joules per kilogram per Celsius degree. All right, And some textbooks want to be more fussy and say 4190 joules per kilogram per Celsius degree. That's fine as well. And I've seen others that which have gone as so specific as 4186. Okay. Again, 2 sig fig, 3 sig fig, that's all you need for here. You don't need to go for significant figures. Student has a question. You can type it away or you can ask away.
Sorry, and that number is the heat capacity of water, or the specific heat capacity of water?
Yep. It's a number that we'll be seeing quite a bit, and that's why I'm pointing it out. All right. It's a number that we'll be seeing rather frequently. Don't worry, you don't need to memorize it. It is available in your course pack. And yes, I'll give you a lookup table on your quiz, test, or exam as well. All right. Now, depending on the textbook that you have, some textbooks will write it out like this. EH is equal to MC delta T. EH for heat energy. But if you go into the world of chemistry, chemistry will rewrite the same formula as Q is equal to MC delta T. Just to maintain the same consistency as the textbook, I'll also go by the letter Q as well. And if you're wondering why in the world did they choose the crazy letter Q, well, when I looked it up, it's because they chose Q for the quantity of heat. All right, so effectively, this formula is stating the quantity of heat required to heat up however many kilograms of water by that special magical number based upon how much the temperature has changed. That's why it's delta T. All right, so delta T is not for change in time, it's for change in temperature. All right, so let's solidify that formula and understand it better by using this example over here. Okay, how much heat energy is needed to heat up 80 liters of water from 15 degrees Celsius up to 24 degrees Celsius? I'll give you guys a moment to jot that down. Okay, let's start answering this question here. Now, one thing we're just going to approximate is that 80 liters of water is roughly equal to 80 kilograms of water. All right. As I mentioned, most of our SI units is based upon water itself. All right. If you wanted to have, for example, 1 liter of fluid, what would you do? Well, you'd build a box. You'd build a box where the dimensions of the box is 10 centimeters for its base, another 10 centimeters for its depth, and then you'll build it to a height of 10 centimeters as well. All right. So as long as you fill up this cube with liquid, so 10 by 10 by 10 vertically, that is also equal to 1 liter. Okay. And another thing just to make a standard is water. Often they use water as a reference for liter. So if you're stuck on an island and you don't have a scale handy, well, then just take a cup, build a box that's 10 by 10 by 10, and then pour that box that's 10 by 10 by 10 with ocean water, and then hope that that's around 1 kilogram. It's not perfectly there because ocean water is salty, but there's also another catch as well. The original definition was based upon water at 4 degrees Celsius. Not sure if you're aware of it, but water is most dense at 4 degrees Celsius. All right. Again, with regards to kinetic molecular theory, molecules are constantly in motion. At higher temperatures, they jiggle a lot faster. So the water at higher temperatures will take up more area, even though it's still in liquid state. But when you cool it down, the water will become more and more dense. And water becomes most dense at 4 degrees Celsius. When you go below 4 degrees Celsius, water is one of those unique types of molecules where they form kind of like the structure of a building. Have you ever seen like a skyrise being built or any big box building? You'll notice that they end up building all these frames around it. And that's what happens to the water molecules. They structure themselves in such a way that they take up more real estate. All right. So as you cool water down, if you do it slowly enough, water will begin to crystallize, form the structure known as a lattice structure, and it'll take up more space. And that's why, guys, before it's wintertime, you're supposed to shut off all the water valves going to the faucets that go into your backyard. If you forget to turn it off from inside the house, if the line freezes, the water will expand, and it might expand in such a way that will cause the copper pipe to burst. So when the ice thaws out afterwards, unfortunately, you have a flood in your basement. Okay. Yeah, if you're able to freeze water very quickly, on the other hand, then you don't need to worry about this crystallization. In fact, there are some places that say they have nitrogen ice cream. Have you ever tried that before? I haven't tried it yet, but supposedly it's the most smoothest of ice cream, and that's because they chill the cream so quickly that the water inside the cream does not have a chance to crystallize and form that sharp, edgy lattice structure, so you have the smoothest ice cream out there. Fun side facts. Anyways, I think that's more than enough time to buy into answering this question here. So yeah, let's work through this. So 80 liters is roughly equal to 80 kilograms. It's not perfect, but we'll just use that as our reference value. Okay, heat capacity of water, we'll just approximate it to, I think we're going to use your textbook's version, which is 4.19 times 10 to the 3, or 4190 joules per kilogram per Celsius degree. Okay, so we have these two values. So far, so good. Third value is delta T. What is that change in temperature? All right, so remember, as I mentioned from the beginning of this course, whenever you measure differences, you always do final subtract initial. That's the standard that we always go by. So if the water finishes off at 24 and starts at 15, then we're going to do 24 minus 15. All right, and 24 degrees Celsius subtract 15 degrees Celsius. I think a lot of you guys will just write down 9 degrees Celsius, which I'll accept. That's perfectly fine. But grammatically speaking, it's changed by 9 Celsius degrees. If you're wondering what the difference is between degrees Celsius and Celsius degrees, well, your house could be set at 24 degrees Celsius right now. And if you find that a little too warm, maybe you want to decrease the room's temperature by another 2 Celsius degrees. All right, so that's the difference between degrees Celsius and Celsius degrees. One is the absolute temperature in a location, and the other one is a relative change. Will I care so much on the test? No, not really, but I'm just letting you know that there's grammar in there as well. Okay, so if you ever see the degree symbol flipped around, that's the reason why it's true. Okay, so the last thing we need to solve for is Q. Remember, guys, in physics class, always stick with MKS. In chemistry, they will use MGS, so please watch out. All right, because in chemistry class, you will see the same formula again, but in chemistry, they're not going to use kilograms, they're just going to use grams. All right, so just watch out for those little nuances there. Okay, so sub everything in, crunch it away. And someone's asking about the degree Celsius and Celsius degree. Again, it's just semantics. I'm not going to be fussy about it. The room is currently at 24 degrees Celsius. That's an absolute measurement, all right? So that's an absolute measurement here. That's an absolute measurement here. If you want to look at the difference in the numbers, then you have a relative measurement, and that's why the degree symbol is placed on the outside. Again, these are just small little grammatical things which I'm not going to be too concerned about in grade 11. But in case if you ever see it flipped around in the future, now you know why it's flipped around. All right, so you'll sub the values in. Again, making sure that mass is in kilograms. And then at the end, you'll have this value. And it's going to be an insanely huge value. 3 times 10 to the 6 joules. Okay, so what is 3 times 10 to the 6 joules? All right, remember what 1 joule is, right? 1 joule is taking that bottled water and just lifting up a measly 20 centimeters, right? By lifting up 20 centimeters, that's 1 joule of energy. This is 3 million, so imagine doing that 3 million times. Okay, now someone was asking about what C is. Again, C is specific heat capacity. Right? Every substance has a different heat capacity value of C, and water is just at 4190 joules per kilogram per Celsius degree. Another good thing, why did I put the plus sign over here? All right, now that it could be a plus sign, it could be a minus sign. As I mentioned, energy is a scalar quantity. All right, so there is no, 6 joules forwards or 6 joules towards the north. You either burn 6 joules or you store it up 6 joules of fat. And if you were to store up 6 joules of fat, then you have a minus sign. So that's what the plus and minus really mean. All right, plus means that this object has now gained thermal energy. You've pushed energy into it. Meanwhile, if you had a minus sign, that means it's lost thermal energy. And you probably would see that if you had water that was originally at 24 degrees and dropped down to 15. All right, so your TF is at 15, but your TI is at 24. And if you subtract these two, you're going to have a temperature difference of negative 9 Celsius degrees. And if you sub that up into here, you're going to end up having a negative value. Okay. Hopefully that clarifies that part there. All right, so I put down the plus sign just to remind you that, yeah, anytime it's plus, it means heat is added to the system. If you want to write that in your notes, by all means, okay? If Q is greater than 0, that's how you indicate anything that's positive, then heat is added. And if you ever have Q that's less than 0 joules, then heat is either released or removed. Either or. Yes, that's pretty cool, isn't it? As we cool something down. Not sure if a pun was intended or not. Oh, I had it already typed out. Oh, boy. All right. Good. Okay. Any other questions? Anyone else still need the slide before I move on? Just a raise of hand if you need a bit more time. Okay. Just drop your hand once you're ready to move on. Okay, thank you. And these are small things you want to think about as well. Not necessarily with heat capacity, but the ability for heat to transfer through something. And you want those values to be rather low. All right, and there are lookup tables for it as well. Water is pretty decent at transferring thermal energy. That's why often we like to use water to cool systems. For example, some of you guys, have computers that are so decked out that they have a water cooling system. And the reason why they choose water is because water is an excellent heat sink. It can absorb a lot of thermal energy and it can transfer it to point B quite readily. Right. So yeah, that's why they use that technology there. Okay, a bit of history here. Okay, as I mentioned, it was James Prescott Joule that which discovered that thermal energy is exactly the same as mechanical energy, and after it was also proven that even electrical energy falls into the same form of energy as well. All right. Again, we want to stick with standard units and standard systems. So Joule developed this crazy-looking machine just to prove that. What's going on over here? Well, there's a physical mass over here, and there's a ruler so you could figure out the height that the mass has fallen. Remember that mass has a certain amount of potential energy, right, which is equal to mg delta h. All right, so there's a string attached to the mass, and it's spun around this axle. And the axle is connected to this paddle that's able to flap around in a circle, which may seem rather bizarre. And to the left over here, that's a thermometer. And this is what Joule proved. And I don't know if you guys ever tried doing this before. Anytime that you end up stirring up food or stirring up any form of liquid, over time the liquid will get warmer. And the science behind that is that as you are agitating the liquid, the molecules are bumping against each other and they're jiggling faster and faster. Right. So anytime that you stir up food, you will increase its overall temperature. And he was able to prove that was true using this crazy invention over here. Right. So he was able to prove that you can convert mechanical energy into thermal energy. And then afterwards, we're able to prove that you can go the other way as well. All right, which is how all heat engines operate, like that in your car. All right. We have a more of a modern day version of it, and I hope that one day you'll be able to experience this again in your local Costco. Say hi to Joe. I really have no idea what his name is. I actually just Google searched, what is it, Vitamix Costco, and then this man's face shown up. So unfortunately, this guy got tagged for it. But if you ever tried out this free sample before, it's pretty crazy, right? The person puts in a bunch of vegetables and then some sort of stock in there. They hit the on button, and then 5 minutes later, you have this piping hot soup. And no, inside there is no coil. There's no heating coil. They're not using radiation or anything else to heat up the liquid. All right. Instead, the reason why the liquid's being heated up is because the blades are moving so quickly that's causing the water molecules to bash quickly enough to actually heat up to a temperature where it's enjoyable as a soup. Okay, so there are real life applications of Joule's apparatus. All right, and that's why for some of those food purists, they avoid using a blender because they know that blenders will heat up the food and may end up destroying some of the nutritional value in the food as well. Okay, again, you don't need to copy the slide over here. It's just a different way of seeing how numbers work. All right. We talked about an isolated system yesterday or last week, all right? Where in an isolated system, this is one where no energy escapes out of the container, no mass escapes. You're not adding any heat into the container. You're not adding any mass to the container. So in other words, whatever that's in there, you mix it up together, and whatever temperature it stabilizes at is whatever you get at the end. Okay? All right. The same is also true when you take an object and you throw it up into the air. Okay? As it's moving up to the air, it's treated as an isolated system. I'm not losing any mass in this ball up here, right? Nor am I adding any more energy. Yes, energy was added before you saw it in the frame, right? So you didn't see my hand throwing it up there. All you saw was just the ball going up by itself, all right? So while the ball is experiencing free fall, which is the path that's going through right over here, the energy remains constant. And since the energy remains constant, it goes constantly to a value of 0 joules, right there. Okay, so this is the proper definition of the formula from last week. It's supposed to be delta EK plus delta EP is equal to 0 joules, right? Because we're not adding any more work to the system. We're just letting it be by itself. So it nets to a value of 0, right? So whatever energy that you may gain or lose in kinetic energy, well, then it'll be distributed to the potential energy, and you're not going to gain anything at the end because you can't invent energy from nowhere, okay? Remember, energy cannot be created or destroyed, but can be converted from one form into another. All right, and that's what this formula effectively does. To prove to you that it does go back to our formula from last week, let's go and expand this out. So delta EK has the same meaning as EKF minus EKI. In other words, 1/2 mv squared minus 1/2 mvi squared. We can treat it the same with regards to potential energy. All right. The difference in potential energy is the final potential energy subtract the initial potential energy. What we're going to do next is that we're going to bring all the values of I to one side and all the values of F to the other side, or swap it around the other way around like this, and you've effectively got the same formula as last week. So in fact, this is the proper way of defining last week's equation. All right, this is the proper backstory to it. However, in grade 11 introduction, all we just simply say is that the total energy at the beginning is equal to the total energy at the end, and the math will just work itself out. Okay, so you don't need to copy this out, but I hope that this gave you inspiration on another way of seeing how to solve these problems. In fact, I'd rather stick with this definition when I describe about temperature. Okay, because some textbooks, all they do is just tell you that Q gain is equal to Q loss minus sign, and they move on without telling you any background story behind it. All right, maybe they'll give you the logic that as one object gains, the other one's going to lose, and that's why there's a minus sign, and that kind of gets the idea across. But let's use this proper definition. Okay, if you isolate a system, then by definition, whatever you have contained in here, if it doesn't escape, then it nets to a value of 0, because somebody's going to gain, somebody's going to lose. Okay, so you can imagine having just a bunch of containers. I know these are filled up, but hopefully you get the idea. You have a bunch of containers filled up with liquids of different temperatures. You pour them all into one big vial, and you know the temperature will eventually stabilize. The cooler substance will heat up, and the warmer substance will cool down, and eventually they will balance out the same temperature. Does any heat escape into the environment? As long as we assume that we have the best container in the universe, no energy will escape. No energy will enter in, and that's why we're going to make it equal to 0 joules. Okay, so the thermal energy is released by one substance plus the thermal energy absorbed by second substance is going to be equal to 0 joules. That's the formula we're going to start off with. Cute little story about Calvin, who's fighting about taking a math. Haha, very cute. Again, the story over here, this is going to be treated either as a closed system or an open system, depending upon how you interpret it. All right. Now, if you're taking the water has a chance to evaporate out of the bathtub, which in real life it will, then yes, you could treat this technically as an open system. Another important thing is that the heat is also emitted off into its environment. All right. So that definitely makes it not an isolated system. All right. So maybe this is not the best example for this problem over here, but you probably have experienced the fact that if the water's too warm and you want to cool down quickly, what will you do? Simply add some cold water. All right. So let's take this problem from that perspective. How much cold water do you need to bring the water down to something that's actually comfortable and enjoyable? Okay. So let's say that this bathtub currently contains 100 liters of water at 30 degrees Celsius. And the question is, how much cold water must be added so that you can end up with a final result of 24 degrees Celsius? Problems like these are a bit easier to solve if you create two sets of givens, right? Because we have two sets of fluids that are in the system, right? We have the hot water and we have the cold water, right? So that's why you'll notice that I have two groupings of givens. All right, so Q is equal to MC delta T. So we have an MC delta T for the hot water and an MC delta T for the cold water. And this is just my recommendation of how to solve these problems. You just start off with this written down. So given MC delta T for item 1, MC delta T for item number 2. Then you populate it in, and at some point you're going to have a question mark. And the question mark is the value that you're looking for. Okay, so we said that 100 liters of water is approximately equal to 100 kilograms of water. Okay, remember this is water that was originally at 30 degrees Celsius, so that's treated as the hot water. Right, so we have 100 kilograms of hot water to start off with. Specific heat capacity of water is at 4190 joules per kilogram per Celsius degree. And if you write down degrees Celsius, it doesn't bother me. All right, I'm fine with that. Every textbook has their own little take on it. Some are accurate to it, and others deviate from those rules. That's fine. Okay, and remember that whenever you do a change, it's always the final subtract the initial, never the other way around. Okay, we want to bring the final temperature of this hot water down to 24 degrees Celsius, but it started off at a tepid 30 degrees Celsius. So 24 subtract 30 will give us -6, and you can write it down as degrees Celsius if you want to, but grammatically speaking, it has decreased by -6 Celsius degrees. All right, next we're going to rinse and repeat with regards to the cold water. Again, it's asking how much cold water, so we don't know the mass yet. That's what we're trying to solve for. This cold water shares the same heat capacity as the hot water, so 4190 joules per kilogram per Celsius degree. Again, delta T is final temperature subtract initial temperature. So yeah, the cold water eventually will elevate up to the comfortable 24 degrees Celsius, but it started off at a frigid 10 degrees Celsius. So 24 subtract 10 will give us 14 Celsius degrees. All right, and there are your givens. And I think I have it all PowerPointed out so it's nice and clean. There you go. There's the tidy edition. Somehow I have a gut feeling I should have inserted a space there. Apologize for that. Okay, next part. We're going to use this formula now. Okay, Q of item number 1 plus Q of item number 2 is equal to 0 degrees, or sorry, 0 joules. All right, Q1, well, I may as well just call it QH for Q of the hot water, and Q2, I'm just going to call it Q of the cold water. That's all. You could still keep it as Q1 and Q2 if you want to, and you can also do your givens as M1s all the way and M2s all the way. Preference is up to you. Student has a question.
For cold water, why is it 24 minus 10?
All right, remember that's the final temperature subtract the initial temperature. Right, we want the bathtub to be comfortable at 24 degrees Celsius at the end of the day. So in other words, the hot water has to cool down to 24 and the cold water has to increase up to 24 degrees Celsius. Hope that answers your question.
So so the cold water started at 10 degrees and then became 24 degrees?
Exactly.
Oh, because you're adding the, okay.
Yeah. I mean, if you need to have 2 separate cups, maybe that will help out, right? You have 1 cup of super hot water, you have another cup of super cold water. You mix them together, you're going to get a lukewarm temperature, right? The hot water is going to cool down. The hot water started off at 30 and finished off at 24. Okay, and that's why I said the order that you subtract it does matter. It's always final subtract initial. All right, so 24 subtract 30, then yeah, the hot water will cool down. But the cold water, starting off initially at 10 degrees Celsius, heated up to 24 degrees Celsius, and that's why it gained thermal energy. So the hot water lost thermal energy, and the cold water gained thermal energy. All right, yeah, Q released plus Q absorbed is equal to 0 joules. We're assuming this as an isolated system. And in all of our questions for homework tonight, it's assumed to be isolated. Okay, we're not going to have a system where mass will start disappearing along the way or that heat was added in. We'll save those adventures for, I suppose, first year university physics. All right, when we talk about thermodynamics. Or if you're in any enriched program, you may learn about that sooner. For example, if you take AP Physics or IB Physics, you'll learn those concepts sooner. Okay, so Q is equal to MC delta T. So we have 2 sets of MC delta T. To differentiate between them, again, you can either call them 1 or 2. In this case, since we have H's and C's, then I'll just use those letters accordingly. Whoops, too many H's on the left. Okay, so MHCH delta TH plus CC delta TC is equal to 0 joules. From here, we're just isolating for MC. So we're going to take this term, bring it all the way to the right, so it's going to become negative, and we're going to divide everything by C delta T. Right, so we're going to get MC, I better write on the left now because I'm going to run out of space. Normally, you're supposed to line up the equal signs. I just know that it's not going to work in my favor this time. Okay, so MC is equal to negative M subscript H, C subscript H, delta T subscript H, all divided by C subscript C, delta T, capital delta T, subscript C. Carefully substitute the values in. All right, and you could type in every number in your calculator, but for some of you sleuths, you might notice that because we're mixing water with water, there really wasn't any need to type in the value C twice in your calculator. So yeah, you do need to show it in your work just so that you and I both know that we're talking about water with water, but on your calculator, you probably want to save yourself that effort. Okay, so you're really on your calculator, you're going to do 100 times 6, which is 600, and 600 divided by 14 gives you an answer of, I don't know, some sort of kilograms that's definitely going to be less than 100 kilograms. 43 kilograms. All right, and we're going to keep it with that. If the question doesn't say it, we assume that they are in an isolation system. Yes, that is correct. All right. Again, as I mentioned, for grade 11, we're just going to take it that it's all isolated. Okay, we're not even going to question it. No problem, right? No trick questions here. Closed system and open system, we'll save that for university. Any other last questions before I stop the recording? Questions that might be beneficial to other students that are watching this feed? All right, if there are any other questions, I'm going to stop the video. And again, for more adventures like this, make sure you like, subscribe, hit that notification button, and I'll catch you in the next episode. Bye for now.